Okay, we can put this one.
What's up, guys? I'm Ethan.
I'm Andrew.
And this is Linear Algebra Trick Shots.
Alright, this is the linear transformation shot.
Whoa, hold up. What is a linear transformation shot? Well, let's think of this graphically. We all know that a linear transformation has the form ax equals b. For this trick shot, we have an easy short target, x1, and we want to transform it into this farther and more difficult shot, b. However, with only one x and one b, there's an infinite amount of A matrices that can transform X into B. So we need a second short target, X2, to sort of calibrate our A matrix. Let's go back to the shot and try these short targets. Now, let's find our A matrix that transforms the short targets into the far target. First, we represent our A matrix with unknown variables like so. Next, we have our two matrix transformations, which can be shown as a system of equations. This can be depicted as a matrix M, which, when row reduced, gives us our solutions in the A matrix.
Okay, now I'm calibrating. Let's go! Let's go! Let's go! Oh my god! Dude, oh my god! Oh my god! Let's go! Dude, oh my god! Dude, oh my god! Let's go! Linear transformations.
This is the basis shot.
Let's go!
Let's go!
Nice,
Let's go!
In this shot, me and Andrew were standing at different locations with a fixed trajectory of our objects, with the goal of hitting them at 11,9. Our trajectory vectors can be placed on the origin as vectors b1 and b2, which form the basis for the column space of A. Using the unique representation theorem, we know that we should find a unique linear combination of our basis vectors to get to our point of collision. Using an augmented matrix and row reducing it, we get our coordinate vector of x relative to b. And this is correct because my vector was scaled by 2 and Andrew's vector was scaled by 3. Let's see another example of this.
Using different basis vectors, we can do the shot again, but with sockets.
That was first try. Like, yeah. Okay, that was too easy.
Okay, so this is the explanation for the pool shot. This shot involves eigenvalues and eigenvectors. So what we're going to do first is define the variables. Our A matrix, which is a 2x2 matrix, has the first row representing the position of the cue ball, and then the second row representing the position of the 8 ball. The eigenvector is represented by the angle of the cue stick, and then our eigenvalue is represented by the power of the shot, and that's determined by how far the cue stick is pulled back and how hard the ball is hit. So this is a visual representation of the shot. If you imagine this pool table as like an XY plane, and then the very center right here as the origin, then we can find sort of the coordinates of the cue ball and the 8 ball in the initial setup. So the cue ball sort of has the points, or has the coordinates 4, 1.5, which is 4 units along the x-axis and 1.5 units up the y-axis. And then the 8 ball has the coordinates 6, 4, which is 6 units along the x-axis and 4 units up the y-axis. And again, these coordinates will represent our A matrix, and that is shown here. So 4, 1.5 will represent the position of the cue ball, and then 6, 4 will represent the position of the 8 ball. Once we have this A matrix, we can solve for the eigenvalues, which is shown in this work here, and we get that lambda equals 7, or lambda can equal 1. For our shot, we decided to use lambda equals 7. And remember, lambda equals 7 is not just how far the cue stick is pulled back, but it also takes into account how much power the ball is hit with. Alright, and once we have lambda equals 7, we can solve for the eigenvector that corresponds to that. And that eigenvector is 1/2, 1. Now, what does this 1/2, 1 sort of mean? It is the angle of the cue stick during the shot. So let me show that right here. If you have the vector 1/2, 1, you might say, how is that represented by the angle of the cue stick here? It is kind of hard to see from this angle, but if you move this up to the origin, just move the cue stick from where it's actually being shot up to the origin, you can see that it actually kind of makes sense. You move half a unit along the x-axis, which is around somewhere here, and 1 unit up to the y-axis, along the y-axis, you'll actually get a vector that's very similar to the angle of the cue stick, right? So let me just move this back. But yeah, 1/2, 1 is just the angle of this cue stick. So now that we have our A matrix, our eigenvalue of 7, and then our eigenvector of 1/2, 1, we have everything we need for this sort of equation to work out and for this shot to go in. And that again is shown here, which is we hit the 8 ball off this side, and then it rebounds off this side, and then off this side, and finally into this pocket right here.
We can do a different shot with different eigenvectors.
Using that same principle, we're going to apply this to soccer. Now that we're calibrated, we're going to go on to the far shot. Let's go!
Absolutely. Dude, oh my god! I swear it's moving. Like, come on. We need to get Justin Hewell over here.
Yeah.
You do it for us.
Wait, Justin's in linear algebra.
Yeah, you wouldn't even know because this guy's gonna come to class in like a month.
Throughout this video, we have a couple people that we want to thank.
The first is Owen, who is Richard's brother, who helped let us borrow a lot of equipment for the football linear transformation shot. He also helped with rebounding a lot of our missed attempts.
We also want to thank the family at Potomac Community Center who kicked after kids and let us use the pool table.
We'd also like to thank Evan Carter, who helped us record the intro and also provided inspiration for this entire video.
We want to thank Ms. Malinowski for teaching us all the basics of linear algebra.
And finally, we'd like to thank you guys for watching this video.